Look around you, what do you see? Perhaps a child on a swing, gently moving back and forth. Maybe you hear the hum of a refrigerator, a subtle vibration, or think of a guitar string plucked and singing its note. These are all examples of oscillations. An oscillation is simply a repetitive motion. It's a wiggle in time. It's a movement that repeats itself over a regular interval, returning again and again to the same positions. The universe, it turns out, loves to oscillate. It's a basic language spoken by matter and energy across the cosmos, a rhythm that underpins so much of what we observe and experience. Light travels as an oscillating electromagnetic wave. Sound is an oscillation of air pressure. From atoms vibrating within a crystal to the universe itself, oscillations are everywhere. Understanding these fundamental wiggles helps us decode the messages the universe is constantly sending us. Learning about them is like getting a backstage pass to how the universe works. Now that we've established that oscillations are everywhere, let's zoom in on a particularly special type of oscillation. It's called simple harmonic motion, or SHM for short. It's the purest form of oscillation, the kind of motion that many systems in nature strive for. In SHM, the restoring force is directly proportional to the displacement from the equilibrium. Imagine a mass attached to a spring. If you pull the mass to the right, the spring stretches and pulls it back to the left. This precise relationship leads to the smooth, regular, and predictable pattern of SHM. Many systems in nature exhibit SHM, especially for small displacements. Understanding SHM is like finding a Rosetta Stone for deciphering many of the universe's rhythmic messages. What does it take for an object to perform simple harmonic motion? There are specific conditions. The first is a restoring force. This force pulls or pushes the system back to equilibrium. Think of it as the object's happy place. When displaced, the force guides it back. The force must be proportional to the displacement. This is Hooke's law for springs. This linear relationship is key. The force scales with displacement. The force must always be directed towards equilibrium, opposite to the direction of displacement. Ideally, resistive forces are negligible. In reality, they damp the oscillations. But we start with an ideal system. To see the pure, undamped rhythm, it's the baseline rhythm. These conditions define the performance. Without them, motion isn't simple harmonic. When an object is performing simple harmonic motion, its position is constantly changing. It moves back and forth or up and down around its central equilibrium point. To describe this motion precisely, we need to talk about its displacement. Displacement is simply the object's position relative to that equilibrium point at any given instant in time. Think of the equilibrium point as 0 on a coordinate system. If the object is to the right, it has a positive displacement. If it's to the left, it has a negative displacement. This value tells us exactly where the object is in its oscillatory cycle. To fully describe the displacement in SHM, we use a mathematical equation. Stands for amplitude. The maximum displacement from the equilibrium position is the angular frequency of the oscillation, telling us how quickly the oscillation is happening, is the phase constant, determining the initial position of the oscillator at time, by adjusting. And we can describe any possible simple harmonic motion. This equation is a powerful tool for understanding the universe's favorite beat. It allows us to predict and analyze these fundamental movements with remarkable precision. Knowing where an oscillating object is, its displacement is crucial. But physics often asks another important question. How fast is it moving, and in what direction? This is where velocity comes into play. In simple harmonic motion, the velocity of the object is not constant, it's continuously changing. Think about a swing. It moves fastest as it passes through the bottom, the equilibrium position, and momentarily stops at the highest points of its arc. We can find the velocity of an object in SHM by looking at how its displacement changes over time. The formula for velocity in SHM is: the term in the velocity equation represents the maximum speed of the oscillator, often called. The velocity is greatest when the object passes through its equilibrium position. Conversely, the velocity is 0 at the extreme points of the motion, or understanding this interplay between position and velocity is key to grasping the dynamic nature of simple harmonic motion. It's a continuous exchange between stillness and speed. We've talked about where the object is, which is displacement, and how fast it's moving, which is velocity. Now let's consider how its velocity is changing. This change in velocity over time is called acceleration. Just like velocity, acceleration in simple harmonic motion is not constant. It's always changing, directing the object's speed and direction. To find the acceleration at in SHM, we can look at how the velocity changes over time. The acceleration is given by at equals negative a omega squared times cosine of omega t plus phi. This equation tells us that the acceleration is directly proportional to the displacement, and its direction is always opposite to the displacement. The magnitude of the acceleration is greatest at the extreme points of the motion, where the displacement x is maximum. Conversely, the acceleration is zero when the object passes through the equilibrium position, x equals 0. Understanding this interplay between position, velocity, and acceleration is key to grasping the dynamic nature of simple harmonic motion. It's a continuous exchange between stillness and speed. An object moving in simple harmonic motion possesses energy. This energy isn't static, it transforms and shifts as the object oscillates. One form of this energy is kinetic energy, which is the energy of motion. The formula for kinetic energy is Ke equals 1/2 mv squared. Since we know the velocity Vt equals negative a omega times sine of omega t plus phi, we can substitute this into the kinetic energy equation. This gives us Ket equals 1/2 ma squared omega squared sine squared of omega t plus phi. Kinetic energy is greatest when the speed is greatest. As we learned, the speed is maximum when the object passes through its equilibrium position, x equals 0. Conversely, when is the kinetic energy at its minimum? It's at its minimum when the speed is 0. This happens at the extreme points of the oscillation, where the displacement is x equals plus a, or x equals minus a. So, the kinetic energy continuously varies from 0 at the extremes of motion to a maximum value as it passes through the equilibrium position. This transformation of energy is a key aspect of understanding the dynamics of SHM. Besides kinetic energy, an object in simple harmonic motion also possesses potential energy. Potential energy is stored energy an object has by virtue of its position or configuration. For an oscillator like a mass on a spring, potential energy is stored in the spring when it's stretched or compressed away from its natural length. The more you stretch or compress it, the more potential energy is stored. The potential energy stored in such a spring system when it is displaced by x from equilibrium is given by the formula Pe equals 1/2 kx squared. Since we know the displacement xt equals a times cosine of omega t plus phi, we can substitute this into the potential energy equation. Pet equals 1/2 k, a cosine of omega t plus phi squared. Potential energy is greatest when the displacement is maximum. This occurs at the extreme points of the motion, x equals plus a or x equals minus a. The maximum potential energy is Pe underscore max equals 1/2 Ka squared. The potential energy varies from 0 at the equilibrium position to a maximum value at the extremes of motion. Notice how this behavior is opposite to that of kinetic energy. When Pe is maximum, Ke is 0, and when Pe is 0, Ke is maximum. We've seen that in simple harmonic motion, kinetic energy and potential energy are constantly changing. When one is high, the other is low, and vice versa. But what about the total mechanical energy of the system? This is the sum of the kinetic energy and the potential energy. E underscore total equals Ke plus Pe. In an ideal simple harmonic oscillator, where there are no dissipative forces like friction or air resistance, this total mechanical energy remains constant. This is a profound and beautiful principle, the conservation of energy. We have Ket equals 1/2 m a squared omega squared sine squared of omega t plus phi, and Pet equals 1/2 Ka squared cosine squared of omega t plus phi. For a mass spring system, we also know that the angular frequency omega is related to the mass m and spring constant k by omega squared equals k over m. Substituting this into the potential energy equation gives Pet equals 1/2 m omega squared, a squared cosine squared of omega t plus phi. Now let's add Ke and Pe. E underscore total equals 1/2 m omega squared a squared times sine squared of omega t plus phi plus cosine squared of omega t plus phi. For any angle, sine squared of angle plus cosine squared of angle equals 1. This means the total mechanical energy is E underscore total equals 1/2 m omega squared a squared. This conservation makes SHM a predictable and beautifully balanced dance, a microcosm of the energy conservation laws that govern the entire cosmos.